Hi, Dr. Na. I have a quick question.
Oh, yeah.
So I wasn't able to attend your full office hour on Tuesday, but I saw that you were recording it. Have you made the recording available somewhere?
Yeah, actually, I recorded the Monday's office hour and I sent that file to Professor Chu. And then, yeah, he's gonna announce to you to get that recorded video.
All right, great. Thank you.
Yeah, Professor Chu.
Yes.
Yeah, Maurice asked about the video recording of the Monday's office hour.
Either recording or the Monday office hour. We didn't have an office hour on Monday. Tuesday we had one by you.
Yeah.
I meant the Tuesday one that Dr. Na had.
Then it's sent to you, right, Dong? It wouldn't be sent to me.
Yeah. Actually, I sent you the shareable link of that.
Oh, you sent me the shareable link. Okay.
Yeah.
Why didn't you send it directly to the student instead of going through me?
Okay, I see. Yeah.
Okay. Yeah, I didn't know that you wanted me to send the link to the student.
Okay, then.
Well, we're more efficient if you just send the link directly to the students.
Okay.
Do you have access to the email list of the students?
I only can access through the Brightspace. Yeah.
Yeah. Don't you also have an email list that you can access?
I didn't have any email list.
Okay. Let me teach you how to get the list. Okay. After class, I'll teach you how to do that.
Okay.
Okay. We can get started now. I see a student by the name of Xiang Tong Kong, but I didn't see you on the registered student list. Are you one of our students? Xiang Tong?
Professor, it's Runzi Hao.
Hello?
Hello? Hello?
Can you hear me? Let me see. Can you speak again, please? Xiang Tong?
Hello? Can you hear me now?
I can hear you now.
Yeah, it's Runzi Hao. I borrowed a computer from my friend. I'm sorry for it.
No. I didn't see your name on the email list. Are you a local or are you an online student?
Oh, I'm saying I'm Runzi Hao. I'm one of I'm on your student list, but it's just another student's computer.
Oh, what is your registered name then? Because I don't see your name on the registered student list. Anyhow, what?
Hello? I'm Runzi Hao.
Oh, you are Runzi Hao. Okay, I see that.
Yeah. I borrow another student's computer. I'm
Okay,
sorry.
you use another student's computer to use Zoom. That's why your name shows up different. Okay, I don't recognize the name. Okay, but I do recognize your other name though. Okay, that's
I'm
fine.
sorry. Oh.
I just wonder who this person is. There's something called Zoom bombing. You know what that is?
I don't know. I don't know.
Okay. Zoom bombing means you attack a Zoom class when it's going on session. Okay, so I thought maybe you are or something. But apparently you're not. Okay. Can you see my screen?
Yeah, we can see your screen.
Okay, good, wonderful. Okay. Okay, let's talk about not Hollow waveguide, but something else. We have to talk about dielectric waveguides first. And so we'll talk about dielectric waveguides. And before we get started, we like to talk about the transverse resonance condition. And we have learned this in the previous lecture, that if you have a generalized reflection coefficient, you can actually let me see what something messed up with my wiring. Okay, we show that when you have something still messed up. Okay, so when you have a layered medium, and then you can look for the reflection coefficient, the wave bounce back and forth inside. And then if this is 1, 2, 3, for instance, then we can say R12 tilde is R12 plus R23 tilde e to the minus 2j beta 2z L2 over 1 plus R12 R23 tilde e to the minus 2j beta 2z L2, where L2 is the length, okay, of this, or the thickness of this slab. Okay, and if we assume that medium 3 goes to infinity, then R23 tilde just becomes R23, which is the local Fresnel reflection coefficient. And the guidance condition is such that R12 tilde goes to infinity when a waveguide mode exists. Okay, because if a waveguide mode exists, then you don't need anything to excite it, and the waveguide mode would just be there, bouncing around. And apparently there'll be some evanescence wave in this waveguide mode, and then incident is zero. Okay, E incident is 0. E reflected is not 0. So if you compare incident to reflected, then R12 is infinity. So one way to look for waveguide mode is to look for when the reflection coefficient goes to infinity, and that is when this denominator is equal to 0. Okay. E to the minus 2j beta 2z L2 is equal to 0. And this is called the transverse resonance condition, also in optics. Okay, in optics, this is usually called the transverse resonance condition. Let me see. Okay. And this is very much like finding the resonant frequency of an LC tank circuit, for instance. Okay, you usually would drive this with the voltage source, but if you set the voltage source to 0, and then yet there's a current flowing back and forth in this LC tank circuit, then we say the system is at resonance. Okay, at resonance, you can have 0 excitation voltage and also non-zero solutions. Okay, so this concept can be applied for a general structure the general structure is one that looks something like this. Okay, let's assume that you have a mode that is propagating in between two layered media. On the right hand side, you have a layered medium. Okay, and then on this side, you have another layered medium. And then you can define R1 to R1 minus tilde for a wave that is traveling like this, okay? And then you can also define R plus tilde for a wave that is bouncing off this side. And we know how to find this generalized reflection coefficient. We already figured out a formula to find this generalized reflection coefficient. Then the guidance condition is very similar to what we had before. The guidance condition is that R minus R plus tilde e to the minus 2j beta, beta, I guess it's called 0, right? Beta tz. Let me call this region T, tz T is equal to 1, okay? So if I call this region 0, I call it region 0, so I should use 0 here. Okay, and this has very good physical meaning, okay? And this is called the generalized transverse resonance condition. Okay, and we can give it the same physical meaning as we had given before, okay, which is that the wave travels, you can say it starts with the, you start with 1, okay, the wave starts with 1 at this place here. And then when it goes from 1 to 2, it acquires a phase. The phase that it acquires is J beta 0 ZT. Okay. And then it bounces off the right interface. Then it will have R plus tilde. And then it goes off from right to left. It acquires another phase. Okay. And then it bounces off the left interface. Okay, so you can track the phase and the amplitude of the wave as it bounces around. And this must become itself. Okay, this is at 5, at location 5. Okay, location 5, then the wave becomes itself again. And this is precisely what the above formula is saying. If you rewrite this, it's just R plus R minus tilde e to the minus 2j beta 0 t equals to 1. Okay, and this is exactly the same formula that we have derived before, using the argument that the denominator of the reflection coefficient of the dielectric set should go to infinity. So except for there is a minus sign here, so this one gave this. This is exactly the same condition as we have just derived using another argument. Can anybody figure out why we have a minus sign here instead of a plus sign, whereas when I did this argument, I came up with the plus sign? Okay, there's no minus sign here, but then I have a minus sign here. Why do I have a minus sign here? Anybody wants to give it a try? Okay, nobody wants to give it a try. Let me give away the answer then. The reason is because if you look at the Fresnel reflection coefficient, R12 is minus R21, okay? R12 is defined as the local reflection coefficient when the wave is coming in, bouncing off like this. R21 is the other one. region 2, region 1, the wave bounces off like this and get transmitted like that. If you look at the Fresnel reflection coefficient, they're very similar to each other, except for the sign difference. That's why we have a minus sign there, okay? So if you don't have any question, I will apply this concept to study a dielectric waveguide. Okay, no question, then apply these concepts to study a dielectric waveguide. And let me look at this special example over here. As I said before, this is a very important waveguide because the operating principle of this waveguide is very similar to that of the optical fiber. Except that when you analyze the optical fiber, it is a cylindrical structure. Okay. Whereas this one, we're just assuming a dielectric slab, which is very simple. And when you solve a problem in the cylindrical coordinate system, you have to use a cylindrical coordinate system, X, Y, Z, and then you will have to define a rho and then a phi, okay? And then you will have to work with Bessel functions. Whereas if you work with Cartesian coordinate system, you just have sinusoidal functions, okay? Bessel functions are like this. Maybe, let me just call it rho. Maybe K rho, okay? And it will look something like this. You will have a peak, and then it will go like this. Okay, this is rho. This is J0 rho, for instance. It will look something like this. Whereas sinusoidal function, a lot simpler. You just sine kx cosine kx, and they look like that, okay? For the sine kx, they are always of the uniform amplitude. Okay, the sine one will look something like this, okay? So they're extremely simple and easier to deal with rather than having to study Bessel functions, which are a lot more complicated. So we solved the dielectric slab problem so that you don't have to grapple with Bessel functions, okay? So we can write down the guidance condition right away. It will be R10, R12, e to the minus 2j, beta 1z. I changed my coordinate system, okay? I changed my coordinate system because in the waveguide, the direction of propagation of the guided mode is always called z. So I picked that to be z, and I picked the other one to be x. So the guidance condition is hence this one over here, rather than putting a beta 1z, okay? And this is the guidance condition, and I like to simplify the problem so that it's more solvable, okay? I want to make region 0 and region 2 the same. R10 is this reflection coefficient here. This is R10. R12 is this reflection coefficient here. And I want to make mu2 epsilon 2 the same as mu 0 epsilon 0, okay? So that region 0 and region 2 are the same, and then the guidance condition would become simpler. Okay? And this allows me to do something simpler, and you can see that this equation or this equation can only be satisfied because if you take the magnitude, will be okay, and this will have magnitude of 1, okay, if beta 1x is real. And this implies that R10 magnitude must be 1, R12 magnitude must be 1. This is at least one possible way that this equation can be satisfied. So right away, we know that some phenomenon must occur in order for this reflection coefficient to have magnitudes of 1. What phenomenon would that be if the reflection coefficients are going to be 1? Anybody wants to suggest an answer? Anybody? So the reflection coefficient would have to be 1. Under what circumstances would this reflection coefficient would have the magnitude of 1?
This will be full internal reflection.
Very good. Total internal reflections. So you must have total internal reflections at the top interface as well as the bottom interface in order for this guidance condition to be satisfied. Okay. So let's assume that there are total internal reflections at the bottom and the top interface. Then there would be a Guth-Hengshon shift that happens. We studied that earlier, which is that the reflection coefficient will be of the form of A minus JB over A plus JB. Okay, because if you recall that the Fresnel reflection coefficient R10 is of the form of mu 0 beta 1x plus, sorry, there should be a minus sign here, minus mu 1 beta 0x over mu 0 beta 1x plus mu 1 beta 0x. This is just a simple Fresnel reflection coefficient, but for total internal reflection to occur, okay, this must become an imaginary number. And hence, if that becomes an imaginary number, then the Fresnel reflection coefficient is of that form. And then it has to have a phase shift, okay? That phase shift can be worked out quite easily, because if there's a pure imaginary number, this will be B, this will be A, and then the phase shift is given by e to the j arctangent of B over A, sorry, B over A with a minus sign divided by e to the j arctangent of B over A. So this is the phase of the numerator. This is the phase of the denominator. And then you can see that this is just equal to that. Okay, and you can work this phase out. And let's assume that beta 0x becomes a pure imaginary number. It becomes a pure imaginary number. Let's assume that it is j alpha 0x, which means that if a wave would be to propagate in region 0, this would become, I should put a minus sign here, okay? And then I will have minus alpha 0x. So the wave would be exponentially decaying in the x direction in this picture over here. Let me see if I can make this bigger so that this would be exponentially decaying in the x direction. And then this is the character of an evanescent wave. So because of that, you can see that your A is equal to mu 0 beta 1x. Your B, okay, if you identify these numbers, would be minus mu 1 alpha 0x. And then you can work out the Guth-Hengshon shift. If I call this the J theta E, okay, if I call this phase theta TE, okay, you can figure out that theta TE would be the arctangent of mu 1 alpha 0x over mu 0 alpha beta 1x, okay, beta 1x, by putting this thing in. And this, of course, we have studied before. It's the Guth Hessian shift. Let me see if I know how to spell Hessian properly. There's a C here. Okay. But the guidance conditions is that this has to be true. So the phase shift coming from the Guth Hessian shift plus the phase shift due to the wave bouncing back and forth must all add up to 2n pi, okay, 2n pi in order for this condition to be satisfied. So we will have the condition that the phase shift from the Guth Hessian shift will be 2 theta TE, because there are two reflection coefficients here. You notice that R10 is repeated 2 times. So the phase shift from the Guth Hessian shift plus the phase shift from the wave bouncing around, okay, which is this other phase shift here, okay, that phase shift. I don't need the 1 there, so I can remove the 1. And this must be 2n pi in order for it to become itself, because this total shift will be, if it becomes that, this is just 1, okay? So this is another way of satisfying the guidance condition, and you can actually work this out. If you go through the detail of working this out, you'll find that mu1 alpha 0x over mu 0 beta 1x is equal to the tangent of n pi over 2. You divide by 4. Actually, what you do is that you take this equation, divide by 4, you get n pi over 2 on the right hand side. And if you take the tangent of this, you will get tangent of n pi over 2 plus beta 1x d over 2. Okay, you get this as a guidance condition. It's just a straightforward algebra. Then how do I solve this equation? Solving this equation is non-trivial. Okay, solving this equation is non-trivial, and let's see how we can solve them. So this is what we call an implicit equation. Okay, and what is the variable here? You notice that beta 0x is beta 0 square minus beta z squared. Okay, beta 1x is beta 1 square minus beta z squared. And beta z is the same in all 3 regions. If you go back to this again, okay, beta z is equal to the same number in all 3 regions. What principle do we call that? If the wave is traveling down this waveguide, and if it has the phase of beta zz, this phase must be the same in this region, that region, that region, and that region. And what condition that we say it was? Anybody wants to give it a try? We imposed this condition when we were studying the Fresnel reflection coefficient and when we were deriving it. And we say that this condition has to be satisfied in order for the boundary condition to be always satisfied. What condition is that? Anybody? Let me see if there's anybody left. I still have 15 students in the class. So 15 people in the audience. So what condition do you call that? Anybody wants to give it a try?
Hello?
Hello?
A phase matching?
Phase matching, very good. This is called a phase matching condition, okay? So phase matching condition says that all the beta z's are the same in all the 3 regions, okay? So beta 0x must be equal to that, beta 1x is equal to that. And what condition do we call this? beta 0 x squared plus beta z squared is equal to beta 0 squared. And then from this one, we get beta 1 x squared plus beta z squared is equal to beta 1 squared. What relationship do we call this? You remember? When we studied plane waves propagating in a homogeneous medium, we come up with similar conditions like this. We say that if you have a plane wave, you have this kind of condition.
This is dispersion relation.
Very good. This is just a dispersion relation, okay? Okay, so we're just using dispersion relations to get these two formulas. And then now you can plug them in. You plug in the definition for alpha 0x is related to beta 0x. So everything can be just written as a function of beta c, both left-hand side and right-hand side. But you cannot solve this equation because it's called an implicit equation. As I said before, an implicit equation, there's no closed form solution. The way to solve this is to use graphical methods, okay? Graphical methods, that means you plot out this equation both on the left-hand side and the right-hand side with one common variable. It turns out that the scholars in this community have decided to plot this both sides using this variable beta 1x, okay, beta 1x. And before we convert this equation into a function of beta 1x, let's do something else. Let's assume that depending on whether n is even or odd, the right-hand side will look like a different function. Let's assume that n is even. If n is even, then you have 2 pi divided by 2, then you have pi. So if you were to add a pi to the argument of the tangent function, what does that become? If your tangent function, you add a value of pi to its argument, does that change the right-hand side? If n is even, okay, you add pi or 2 pi or 3 pi, it becomes itself, okay? So it's a piece of cake, nothing happens. What happens if n is odd? If n is odd, if you add pi over 2 to the argument of a tangent function, what does that tangent function become?
Oh, shift by
It's called
half.
tangent.
Cotangent, very good. I hear some good answers, okay? So when n is equal to even, okay, the equation would be something like mu1 alpha 0x equal to mu 0 beta 1x, always having a tangent of beta 1x d over 2 on the right-hand side, okay? But whereas if n is odd, the tangent becomes a cotangent. If you do things very properly, you find that there's an added minus sign as well, okay? So you have two families of equations, okay? And it turns out that the community of scholars have decided to plot this as a function of beta 1xd because this function is a lot easier to plot if we plot it as a function of beta 1xd. And by some simple rewriting, you can actually write the first equation, the n even one, as mu1 over mu 0. Did I get it right? No. Sorry, it should be mu 0 over mu1 beta 1x d over 2. Okay, I just multiply by d over 2 and then tangent of beta 1x d over 2. And then this is purely a function of beta 1x. And then the right-hand side, because of my multiplication and division, will be just d over 2 because I multiply by d over 2 on the other side. This is n even case. And then for the n odd case, I will have minus mu naught over mu1 beta 1x d over 2 cotangent beta 1x over 2 is equal to alpha 0 d over 2. Okay, so you can only solve this equation simply by graphical methods. Okay, at the time, they did not have very good computers and they did not like to use computers, but these days, you might prefer to use computers to solve this problem rather than using graphical methods. But graphical methods are great because they offer you great physical insight. Okay, so we would like to make the right-hand side a function of beta 1x d as well. And to do that, what you do is that you notice that beta 1x square is equal to beta 1 square minus beta z square, as I said before. And then you also notice that beta 0x square is beta 0 square minus beta z square. Okay, that actually I got from here, above there. And then subtract these two equations. Okay, this beta 0x is just actually minus alpha 0x squared because of this relationship I had previously. Where is that relationship? The relationship must be somewhere here. Okay, this relationship. Beta 0x is just equal to minus thing. And then now I can subtract the two equations. If I subtract the two equations, okay, subtract them, and I will get beta z to cancel from each other. And then I will show that quite easily. Alpha 0x squared is omega squared mu 1 epsilon 1 minus omega squared mu naught epsilon naught. Those are the betas of the respective region, beta 1x squared. Okay, I can show this to be true quite easily, which means that the right-hand side, alpha 0x here, can always be expressed in terms of beta 1x. Okay, and then now you can plot the left-hand side and the right-hand side separately. Okay, that's what this is showing. Okay, you plot y1, which is for the even modes. You plot y2 for the odd mode. Okay, and then you plot the right-hand side, which is this equation over here. So if you were to look at the right-hand side is this equation over here, and then alpha 0x squared is given by this, and if you take the square root of this equation, you will have something that looks like this. Okay, so the right-hand side is given by this equation as a function of beta 1x. But if you look at this equation, if I take the vertical axis in this plot to be either y1, y2, or y3. Okay, I plot y1, y2, and y3 as a function of beta 1x. I will get three curves. Okay, the first curve is, of course, y1, which is given by this family of curves here, and then y2, which is given by the dotted curves. And then I get y3. y3 is actually the equation of a circle. I don't know if you see that. Okay, if you look at y3 square, it is given by a constant. If we square this equation, you get a constant, okay, square minus beta 1x d over 2 squared. Okay, so this is actually an equation of the circle. That's why I have this circle over here. Okay, and then the solution to this equation will be the intersection points of the curves. Okay, intersection points of the curves, and those are your solutions. And you find that if the frequency is low, okay, the radius of this curve, if omega is very small, the curve will become one, or the circle will be one with smaller and smaller radius. Okay, it might be like this even. Okay, in that case, there's only one solution. However, if you make the frequency large, the radius becomes bigger and bigger, and you will find more and more solutions. Okay, there's one salient feature, which means that you will find more guided modes for a higher frequency case. For low frequency case, you have only one guided mode. And you can make the frequency as low as you can, as low as you want to be. This radius will become very small, okay? And that means that this mode has no cutoff. No matter how low the frequency is, this mode is always there. And this is called a TE0 mode in a dielectric slab waveguide, and there's no cutoff, okay? Whereas the TE1 mode, after a while it disappears. It cannot be there anymore, okay? So this one has a cutoff, and you can say the same of the other one, okay? So one way to increase the number of modes in a dielectric slab is increase the frequency. Another way to increasing the radius, what other two ways can you make this number large? If I make that number large, the radius of my circle becomes bigger. I will have more solutions and more guided modes. What are the other two ways that I can have as a good engineer to increase the radius of this circle? Okay, anybody wants to volunteer by staring at this curve and saying that actually it's the radius of the circle? What other two ways do I have? Anybody? Make sure that nobody is sleeping and that I still have 15 people left. Anybody wants to try? By the way, are you following the lecture that you have to solve this problem graphically? And there are three curves that you have to plot because of the two cases. The two equations have the same right-hand side, okay? The two equations are the same right-hand side. So this you can just deal with by plotting a circle, but then on the left-hand side, you have two possibilities. That's why we have three families, three sets of curves here, okay? And the solution is given by the intersection point of the right-hand side curve with either one of the left-hand side curves. Okay, we have expressed all of them as a function of beta 1x. Okay, the right-hand side curve is the one that changes with frequency, because if you look at alpha 0x, it depends on frequency in this manner. Okay, only the right-hand side plot depends on frequency. Okay, and then you can change the frequency to change the radius of this circle. What other freedom or design freedom do I have to make this radius of this circle bigger and bigger? Anybody wants to try?
Wouldn't it be in the engineering
material.
your mu1 epsilon 1?
Yeah, I would try to make the contrast bigger. Okay, the outer medium is mu naught epsilon naught. The dielectric medium, dielectric slab, I will make this number bigger. Okay, then that will make the radius bigger. I will have more solutions and more guided modes. What is the last device that I have to make the radius bigger?
Change the width of the waveguide.
Yes, very good. Change the thickness of the slab. That is what D is. Okay, if you go and look at the D case, D is just the thickness of the dielectric slab waveguide. And if you make it bigger, you will have more and more solutions. Okay, so there are three things. These are three salient features: making frequency high, making the contrast big, making the dielectric slab thick. All would increase the number of guided modes that you have in this waveguide. These three salient features are shared by the optical fiber waveguide as well. Okay, so the three salient features. Okay, increase the frequency, increase the contrast, increase the thickness. Okay, so if you make the optical fiber bigger, you will also have more guided modes. And if you increase the contrast, epsilon 1, epsilon 0 outside, you will also have more guided modes. And then if you increase the frequency, you also have more guided modes, okay? Any questions so far? So you can actually go about solving those solutions graphically or using a computer. And then after that, you find your beta 1x. Beta 1x, remember, is the same as, let me see if I can remove this one. Okay, beta 1x and beta z are related anyhow. So beta 1 square is equal to beta 1x square plus beta z square. So once you found your beta 1x, you can find your beta z, and then you can change your frequency to map out the beta z's of different guided modes in the slab. Okay, you'll find that as the frequency gets bigger, like for instance, if you pick this operating frequency, okay, you will have 3 guided modes in this case. Oh, sorry, just 2 guided modes. Here you have 2, or maybe 3. I forgot this one. This one will go up there. Okay, you have 3 guided modes. And if you lower the frequency, then you have only 1 guided mode. Okay, and you can map out this dispersion relationship. So if I want to find the phase velocity of this guided mode, what do I do? If I found a solution here, and if I know beta z is over there, what do I do to find the phase velocity of that guided mode? Anybody? V phase is? Anybody? What is the phase velocity of this wave?
Is omega over beta.
Very good. Omega over beta z. Okay, that is the phase velocity. What about the group velocity? If I want to know, so you just take omega over beta, which is the reciprocal of this slope. Okay, you take this line and you find this slope, be omega over beta z, and the reciprocal of this slope will be the phase velocity. What about the group velocity? What do I do to find the group velocity of this guided mode? Anybody? What is the formula for group velocity that we went through great length in deriving?
So it's differential of the frequency over beta.
Very good. Okay, we went through great labor and great pain to show that by Taylor series expansion and that kind of thing, the envelope of a wave packet would move with this group velocity. Okay, so we can think of this as a wave packet velocity. Okay, and you can see that this group and phase velocity will have all this interesting behavior, and I can give you physical explanation for why they behave like that in the lecture notes. Okay, I wouldn't go through them over here, and you can do that for all the modes. And Professor Kong has solved this modes using computers, and he has very nice curves, and all these dispersion curves will look something like that for both TE and TM case. So you can repeat the analysis for TM modes as well. They're very similar. Instead of using the TE reflection coefficient, you will use the TM reflection coefficient. You find that all these modes have the property of hugging this line, okay? And you can give physical explanation as to why they do that. And then after having obtained the modes, you can also plot for the profile of the field inside, because you know after you have found the beta 1x, okay, then you find that the wave inside would be something like cosine of beta 1xx inside, or plus sine of beta 1xx inside, and they will have different coefficients to be linear superposed together, and you can have all these modes that you find. The TE0 mode will be symmetric. T1 will be odd. And then outside will be e to the minus j, it will be evanescent outside. So it'd be beta 0xx kind of thing. Sorry, alpha 0xx kind of thing, okay? And you can actually find all these decay constants outside and have this curve plotted. Any questions? Any questions so far? Anybody have any questions?
I have a question on how do those modes interfere in that waveguide?
Okay, how do they interfere? What do you mean by that? They will be guided. They will be guided and propagating in the z direction, but in the transverse direction, they will be like a standing wave. They become cosine or sine. Okay. So we first assume that we have a guided mode. Okay, that this guided mode is propagating like this. And then it will be bouncing back and forth in this dielectric slab by total internal reflection. So they will interfere and form standing wave. These are truly standing wave. This standing wave can become either a sine or a cosine function in between the slab waveguide. So they interfere with each other to become a cosine standing wave or a sine standing wave. And that's why you see over here. This is a cosine. This is actually a sine. Outside, they'll be evanescent. They'll be decaying. Okay? Is that good enough answer for you?
Yeah, I see the physics. Thank you.
Okay, very good. Okay, so let's move on to hollow waveguide then. Okay, hollow waveguide is very interesting because it is guidance by a completely different physics. In the previous waveguide that we have studied, we use total internal reflection to guide the wave. So the wave is evanescent here, evanescent here, evanescent here. The wave just bounces back and forth by total internal reflection. But then for a metallic waveguide, you can make this out of metal for a very simple case, parallel plate waveguide. Then the wave just bounces off because it's a sheet of metal and it has to repel the energy from the incoming wave. And this is actually just a simple parallel plate waveguide. Okay, you can actually get this parallel plate waveguide from the previous guidance condition that we have studied before. We would have 1 equal to R10 square e to the minus 2j beta 1x d. Okay, this was a guidance condition. But what does R10 become for a metallic plate? Do you know? If you have a metallic plate, it will be very similar to the reflection coefficient of a transmission line, where the voltage is 0. Okay, what is gamma L for this problem? You send in a wave, the wave will come back at you, completely reflected. And do you know what the reflection coefficient for a short is?
-1.
Very good, -1. Let me see, my phone is ringing. It's usually a scam call, okay? So by the same token of analogy between metal, parallel plate waveguide and transmission line, the reflection coefficient will be -1 for TE wave. It will be +1 for TM wave. So this just becomes e to the minus 2j beta 1xd. And then you can actually work out the guided mode of a parallel plate waveguide quite easily using the knowledge you have just learned in dielectric waveguide. So, but we are going to study not just parallel plate waveguide, and two of the waveguides I'm going to cover in this course is a rectangular waveguide and a circular waveguide. These are simple enough to consider, but these are all metallic. Okay, metallic inside. Okay, so TE case is when EZ equals 0, hz not equal to 0. I don't know how to make not equal in my software over there. So they're supposed to be not equal there. Okay. So the first thing before I proceed, I like to argue that if I have a hollow waveguide, there couldn't be a TEM mode. And I like to argue this using the Latin symbol or Latin phrase, reductio ad absurdum. If people do study Latin still, okay, this is just a statement of proof by contradiction. Okay, how can we prove by contradiction that a TEM mode cannot exist? TEM means it's both TE and TM, and EZ equal to 0, HZ equal to 0, okay? It's a combination of these two cases. And we like to prove that that mode cannot exist inside a hollow waveguide. So let's start by assuming that there's a mode that exists with a magnetic field. The magnetic field of that mode must look something like this. That is, the magnetic field must start and end on itself. Okay, no magnetic charges. Okay, magnetic field must look something like that. Whereas for electric field, it doesn't have to look like that. Electric field might start with a positive charge on the waveguide wall and then end up with a negative charge on the other side of the waveguide wall. Okay, so electric field will look something like this, but magnetic field has to close on itself. But then if you were to perform this integral h dot dl on this magnetic field lines, on this contour C, okay, is this going to be a positive number, 0, or negative number? If you just stare at this magnetic field and perform this integration in your head, okay, dot with a dl, you can do it numerically, plot a dot with a dl, and then take it around this contour and sum this up. What would this number be? Would it be a positive number or a negative number? Or what do you think it should be, or 0? Anybody? H dot dl, what should it be? Ampere's law. If you were to have a piece of wire, if it carries the current, it produces a magnetic field H dot dl. Okay, what should that thing be? Ampere's law. What?
Should be 0.
Should it be 0? You think the H dot dl in this picture over here should be 0 or not? Should it be 0 or not? The magnetic field is always pointing in the same direction as your dl as you integrate. This dot product is always going to be a positive number. And you're going to add up a whole bunch of positive numbers. And it will always be a positive number. Agree or disagree? Or should it go to 0? You can go back to your freshman physics and try to recollect this case over here. H dot dl is not going to be 0, which means that H dot dl is not going to be 0. It's going to be a positive number. But we know that this thing, by Ampere's law, the left-hand side is just Ampere's law, okay, that this is equal to the flux dot ds plus the current J dot ds. Okay, I'm just writing Ampere's law in integral form. You could have written Ampere's law in differential form. Okay, differential operator form, you get that, and then you get that. Okay, so the left-hand side is not 0. So the right-hand side must somehow be also not zero. Okay, but this waveguide is hollow. It's hollow, it doesn't carry a current through it. Okay, S is this surface over here. Okay, so this means that this term must be zero since there's no current going through that surface. Okay, the only way that the right-hand side not be zero is for this term not to be zero. Agree? Since the left-hand side is not zero, the right-hand side cannot be zero. Okay, so S is that surface over there, and N hat is Z hat in this surface. So what do you know about dz? Is it equal to 0 or not equal to 0? Okay, anybody? Is dz 0 or not 0 in this waveguide, hollow waveguide?
It would depend if you're in the TE case or the TM case.
Well, I'm saying that if I just plot the field, I'm not even distinguishing these two cases. You're correct. Okay, you're jumping ahead and went to the TE case. For a general case where the magnetic field looks like that, is dz 0 or not 0? Because I'm searching for a TEM mode. Okay, I'm searching for a TEM mode. So I draw the field for a TM mode where the magnetic field looks something like that. I'm trying to argue to see that if this mode can be both TE and TM, and apparently I cannot because dz cannot be 0. If dz had been 0, this integral would go to 0, and I will have a contradiction, and it's not possible. Okay, so the only way for this contradiction not to exist is for dz not to be 0. Okay, if dz is not 0, that means that this mode cannot be there. Okay, you cannot have a TE mode. So the only kind of waveguide mode you can have is TM or TE, but not TEM. Okay, so a TEM mode cannot exist in a hollow waveguide. That is proved by reductio ad excidum. Okay, so now that we know that the mode inside the waveguide is either TE or TM, we can go about solving for those modes. And let's begin with the TE case. Okay, TE case, then EZ equal to 0 and HZ is not equal to 0. And some people call this TE to Z case, just to be more specific. Okay, so how do I write down the mode of a waveguide arbitrary shape? Okay, that the waveguide is always supporting a TE mode. I use what is called the pilot vector potential approach. And in this case, what you do is that you design an electric field that is curl of a vector potential, okay, that only has a Z component. Okay. And if you were to take the curl of this function, sorry, this is not a function of Z, but a function of R. Okay. If you were to take the curl of this function, can you see that EZ equal to 0? EZ has to be 0. Can anybody give the explanation as to why EZ has to be 0? Anybody? Why does EZ have to be 0?
So because it's, oh no, I don't know.
Well, I can do the long algebra. Okay, you can work out the long algebra, write up the del operator. Okay, and then when you do the algebra, you find that there's no z component, right? It's just a simple algebra, the same as A cross Z. You just do this simple algebra. That means that if I call this vector C, Z dot C must be 0. Okay, if you plug this and do the algebra, it's the same as the algebra that you need here, and EZ will be 0. Okay, is this clear to everybody? Why, if I design a vector potential in this manner, this E does not have a Z component? Okay, is this clear?
Yes.
Okay, very good. Then I can move on. And then is it also clear to everybody the divergence of E equal to 0? Okay, this is a source-free region. It's a waveguide, source-free. Okay, and is it clear to me or to you why divergence of E equal to 0? Because if it's source-free, this has to be true. So any solution that I try to construct has to have divergence of E equal to 0. Can you see why divergence of E equal to 0? Can anybody tell me the important theorem or important algebraic theorem or knowledge that you have that immediately shows you that divergence of E equal to 0?
Divergence of the curl is 0.
Very good. Divergence of a curl is always equal to 0, okay? Very good. Divergence of curl of anything. Okay, anything. Very good. It's equal to 0. And this is for the same algebraic reason, that A dot A cross A equal to 0. Okay, of course, you use the geometric argument to say this. Okay, A cross A gives you something that's orthogonal to A, and then when you dot it with itself, then it's always equal to 0. You can use algebra to prove this as well. And the algebra that you need to prove this is exactly the same as the algebra that you need to prove that. Okay, divergence of a curl equal to 0. The curl of a gradient is also equal to 0 for the same algebraic reason. Okay, so divergence of E equal to 0. So I have constructed a solution which is TE, manifestly TE, and manifestly for a field in the hollow waveguide, which is force-free. Okay, then what I need to do then is to make sure that this electric field solves Maxwell's equations. Okay, so what I do next then is that from Maxwell's equations, I have Faraday's law. And then I will have Ampere's law. Okay, and I can take the curl of this equation, and then I will have curl of H on the right hand side, and then I plug that back in. What I get then is that curl of E on the left hand side would be equal to minus j omega mu curl of H, and then I use the second equation to plug back on the right hand side. I will get this to be omega square mu epsilon E. Okay, and then E must satisfy this equation in order for it to satisfy Maxwell's equations. Let me just write it like this first. Okay, when I have a double curl, again, I can use the back of the cat formula to convert this into divergence, gradient of divergence minus the Laplacian of E. Okay, we did that several times already in this course. And divergence of E is equal to 0. So we can drop this term and finally show that this equation that we have, okay, will become just an equation like this. So in order for E to satisfy Maxwell's equation, E must at least satisfy this equation, which is called the Helmholtz equation. Okay. And then now I can plug in my guess, my constructed E, and plug it in there. And if you plug your constructed E into this thing, what you find is that it's just plugging in, okay? I'm going to skip a few steps here. Just plug in and exchange the order of integration and differentiation. And so you will have something like the equations to be satisfied would be something like curl cross Z psi H is equal to 0. Okay. And then I'm going to exchange the order of this operator and this operator. Okay. In mathematics, we say if two operators are commuting, this is called a commutator. You can think of them as matrix operator if you want to. And this is 0, it means that A dot B equal to B dot A. Okay. When the commutator of two operators is 0, we say that the two operators commute. And you can very easily show that these two operators commute because they commute in this fashion. And hence, I can actually bring the operators inside and take the other operator outside. Is equal to 0. Okay. And then if I find size of H that satisfy this equation, if I make sure that all the size of H that I have satisfies this equation, and if this equation is satisfied, it means that this equation is satisfied. It means that that equation is satisfied. It means that the electric field that I have constructed in this manner using the pilot vector potential, okay, would satisfy Maxwell's equation. Okay, you work backward and make sure that this satisfies the Maxwell's equation. Okay, so we have a PDE. This is called the PDE, or the partial differential equation. Okay, but then we cannot solve an ODE or a PDE without imposing boundary conditions. So we need boundary conditions. Size of H, okay, in order to solve this PDE. And we divide the waveguide into TE case, which is what we have here. For the TE case, if I have a metallic waveguide, what is the boundary condition on the wall of the waveguide? If the waveguide is a PEC. PEC here stands for perfect electric conductor. Does anybody recall? If I have a PEC, what boundary condition should I have on the PEC surface? Does anybody recall? We have only 4 boundary conditions. For electrodynamic problems, we only need to solve 2 or 4 Maxwell's equations. So from 2 first equations of Maxwell, what are the 2 boundary conditions that we have? We have, like from Faraday's law, N cross E continuous. This is from Faraday's law. And from Ampere's law, if there's no current sheet, N cross H continuous. Okay, but what is N cross E inside the PEC surface, inside the perfect electric conductor? What is N cross E inside?
It should be 0.
Right, so N cross E is continuous. So N cross E should be what value on the waveguide wall? Okay, N cross E, somebody already gave the answer away. The N cross E has to be 0 inside this PEC. So since N cross E is continuous, what should it be on the waveguide wall?
Should be 0.
Should be 0 too, okay, very good. N cross E equal to 0 on the waveguide wall. This is the boundary condition that we should have when we solve this equation that we have of solve Maxwell's equations in order to find the solution inside, okay? So let's see what else can we say. Okay. So if n cross E is equal to 0, and on the waveguide wall, but E by construction is curl cross Z of psi equal to 0. And then we have to apply the back of the cat formula again. You call this A, B, C. But when you apply the back of the cat formula, you better make sure that this is an operator and you have to put it in the correct position when you apply this formula. So if I say that this is the back of the cat formula, so the del C dot n psi, the minus cat would be Z n dot del psi. Okay, then that has to be 0. But what do you know about Z dot n on the waveguide wall? You have a waveguide, Z is pointing out like this. On the waveguide wall, what should Z dot n be equal to?
They're orthogonal, so 0.
Okay, very good. Z and n always are orthogonal on the waveguide wall, so this should be 0. And then you will have n dot grad phi equal to 0 on the waveguide wall, okay? This is called a normal derivative. It can also be written in this manner, or sometimes it's written in this manner, okay? So the boundary condition that we have translated to for the scalar potential, the vector potential, the scaling factor would be that we solve this ODE for C sub H is equal to 0 with the boundary condition that this is equal to 0. This is called the Neumann boundary condition, okay? Then we can repeat the same case for TM case. TM case, you go through the same exercise, then H is very close to being the dual of the TE case, and then we put the size of E over here. And then you go and derive that, you can show that size of E will satisfy an equation like this inside the border of the hollow waveguide. But what boundary condition should size of E satisfy? Well, in order to satisfy that boundary condition that it should have on the waveguide wall, you go back and look at the fundamentals again. The fundamentals is that n cross E is equal to 0 on waveguide wall, okay? But E is not given explicitly for this case. So you will have to find E. Okay, E will be proportional to curl of H, will be proportional to curl cross curl of Z psi E. And then you can use the back of the cat formula again. It will be gradient of the divergence of Z psi E minus the Laplacian of psi E with a Z somewhere hanging around with the back of the cat formula. And this one would just give you, using this equation over here, minus beta squared psi E. And this one, okay, and we want n cross E to be 0. You can easily show that if psi sub E is equal to 0 on waveguide wall, okay, this term would be 0. But you can also show that this term would also be 0, okay, because if something is 0 on the waveguide wall, what you're doing here is that when you take the n cross, you're taking the tangential derivative instead of the normal derivative. You're taking the tangential derivative. Here we have a normal derivative. Okay, this is called a normal derivative. This is called the tangential derivative. And if the function is 0 on the waveguide wall, its tangential derivative would also be 0. Okay, so if this is true, then n cross E is equal to 0. So for the TM case, you solve this equation with this boundary condition on C, on the waveguide wall. This is called the Dirichlet boundary condition. Okay, it's called the directly boundary condition. And then you can actually apply this knowledge now to solve for the rectangular waveguide case. I don't have time to go through the rectangular waveguide case. The great thing about it is that so I don't have time to go through the rectangular waveguide case. I'll go through it in the next lecture then. Okay, so I'll stop here. Are there any questions regarding this guidance by polar waveguide? So I've derived this boundary condition, and next time we specialize it to rectangular waveguide, and then even doing the other spherical circular waveguide if you can. But any questions before we end here? Okay, I guess we can stop here. I'm going to hold an office hour at 3 o'clock this afternoon. Let me give it like 3:05 so they can take a break before I hold the office hour. Okay, I'll stop here, and I can send out the office hour link, or I can use the same link. Okay, let me see what I should. I stopped sharing this. I'll see you at office hours then if you want to come for